Register transfers and micro-operations. Learning objectives. In this chapter, the user would learn the following in detail. Bus and memory transfers. 3-state bus buffers. Binary adder. Binary incrementer. Arithmetic circuit. Logic and shift micro-operations. ALU. Register transfer. Designate computer registers by capital letters to denote its function. The register that holds an address for the memory unit is called MAR. The program counter register is called PC. IR is the instruction register and R1 is a processor register. The individual flip-flops in an n-bit register are numbered in sequence from 0 to n-1. The numbering of bits in a 16-bit register marked on top of the box. A 16-bit register partitioned into two parts. Bit 0 to 7, symbol L low byte. Bit 8 to 15, symbol H high byte. Information transfer from one register to another. A register transfer is indicated as shown. In this case, the contents of register R2 are copied or loaded into register R1. A simultaneous transfer of all bits from the source R1 to the destination registers R2 during one clock pulse. Note that this is a non-destructive, that is, the contents of R1 are not altered by copying or loading them into R2. A register transfer such as R5 to R3 implies that the digital system has the data lines from the source register R5 to the destination register R3. Parallel load in the destination register R3. Control lines to perform the action. Refer to figure for the different representations of a register. Designate information transfer from one register to another by R2, R1. This statement implies that the hardware is available. The outputs of the source must have a path to the inputs of the destination. The destination register has a parallel load capability. The content of the source register R1 does not change after the transfer. If the transfer is to occur only under a predetermined control condition, designate it by if P equals 1, then R1 to R2, or P R1 to R2, where P is a control function that can be either 0 or 1. Every statement written in register transfer notation implies the presence of the required hardware construction. It is assumed that all transfers occur during a clock edge transition. All micro-operations written on a single line are to be executed at the same time. Basic symbols for register transfer. Bus and memory transfers. A bus structure consists of a set of common lines, one for each bit of a register. Digital computer has many registers and path must be specified to transfer information from one register to another register. Rather than connecting wires between all registers, a common bus is used. Control signals determine which register is selected by the bus during each transfer. Multiplexer is used to construct a common bus. Multiplexers select the source register, whose binary information is then placed on the bus. The select lines are connected to the selection inputs of the multiplexers and choose the bits of one register. The construction of a bus system for 4 registers is shown. Construction of a bus system. A bus system for 4 registers. Each register has 4 bits, numbered 0 through 3. The bus consists of 4x1 multiplexers, each having 4 data inputs 0 to 3 and 2 selection inputs S1 and S0. Function table for bus. General design issue of a common bus system. In general, a bus system will multiplex k registers of n bits each to produce an n-line common bus. This requires n multiplexers, one for each bit. The size of each multiplexer must be k into 1 since it multiplexes k data lines. The number of select lines required is log k. For example, a common bus for 8 registers of 16 bits each requires 16 multiplexers, one for each line in the bus. To transfer information from the bus to a register, the bus lines are connected to the inputs of all destination registers, and the connecting load control line must be activated. Rather than listing each step as 3-state bus buffers, instead of using multiplexers, 3-state gates can be used to construct the bus system. A 3-state gate is a digital circuit that exhibits 3 states. 2 of the states are signals equivalent to logic 1 and 0. The third state is a high impedance state. This behaves like an open circuit, which means the output is disconnected and does not have logic significance. Design issue. The 3-state buffer gate has a normal input and a control input which determines the output state. With control 1, the output equals the normal input. With control 0, the output is disabled and the gate goes to a high impedance state. The construction of a bus system with 3-state buffers is demonstrated in figure shown. The outputs of 4 buffers are connected together to form a single bus line. Binary adder. A binary adder is a digital circuit that generates the arithmetic sum of 2 binary numbers of any length. A full adder adds 2 bits and a previous carry. Design procedure. A binary adder is constructed with full adder circuits connected in cascade. An n-bit binary adder requires n full adders. The n data bits for the A inputs come from one register R1 and the n data bits for the B inputs come from another register R2. The sum can be transferred to a third register or to one of the source registers R1 or R2, replacing its previous content. A 4-bit parallel binary adder. The purpose of this adder is to add 2 4-bit binary integers. The addend inputs are represented A0 through A3. The organ bits are represented B0 to B3. Consider the addition of the following 2 4-bit binary numbers. The sum should therefore be S3 equals 1, S2 equals 0, S1 equals 1 and S0 equals 0. Here A0, B0 are the least significant bits and they cannot receive any carry from a previous stage. From above example, A0 and B0 are both 1s. Their sum is therefore 0 and the carry is generated and added into the full adder for bits A1 and B0. Similarly, next stage bits are added. Finally, both inputs A3 and B3 are equal to 0 and the carry from the previous stage is 1. Therefore, the output S3 is 1. Binary incrementer. The increment micro operation adds 1 to a number in a register. Example, if a 4-bit register has a binary value 0110, it will give 0111 after it is incremented. This can be implemented by using a binary counter. Every time the count enable is active, the count is incremented by 1. If the increment is to be performed independent of a particular register, then use half adders connected in cascade. One of the inputs to the least significant half adder, HA, is connected to logic 1 and the other input is connected to the least significant bit of the number to be incremented. The output carry from one half adder is connected to one of the inputs of the next higher order half adder. The circuit receives the 4 bits from A0 through A3, adds 1 to it, and gives the incremented output in S0 through S3. An n-bit binary incrementer requires n half adders. Arithmetic circuit. Each of the arithmetic micro-operations can be implemented in one composite arithmetic circuit. Design issue. The basic component of arithmetic of an ALU is the parallel adder. A parallel adder is constituted of number of full address. Different types of arithmetic outputs can be obtained by controlling the data of input to the parallel adder. Multiplexers are used to choose between the different operations. A 4-bit arithmetic circuit. The logic diagram for the arithmetic circuit that performs the various arithmetic operations is as shown. By controlling the value of y with the two selection inputs S1 and S0 and making Cin equal to 0 or 1, it is possible to generate the 8 arithmetic operations. It has 4 full adders for 4-bit adder and 4 multiplexers for choosing different operations. There are 2 4-bit inputs A and B and a 4-bit output D. The 4 inputs from A go directly to the X inputs of the binary adder. Each of the 4 inputs from B is connected to the data inputs of the multiplexers. The multiplexer's data inputs also receives the complement of B. The other 2 data inputs are connected to logic 0 and logic 1. Logic 0 is fixed and logic 1 is through an inverter whose input is 0. Input carry Cin goes to the carry input of the FA in the least significant position. The output of the binary adder is calculated from the following sum: D equals A plus Y plus Cin. Arithmetic circuit function table. Logic circuit. Each of the logic micro-operations can be implemented in one composite logic circuit. General consideration to logic circuits. Logic micro-operations. Special symbols. List of logic micro-operations. Logic micro-operations. Logic operations specify binary operations for strings of bits stored in registers and treat each bit separately. Example, the XOR of R1 and R2 is symbolized by example, R1 equals 1010 and R2 equals 1100. 1010, 1010, content of R1. 1100, 1100, content of R2. 0110, content of R1 after P equals 1. Logic micro-operations, special symbols. Symbols used for logical micro-operations are: the logical disjunction sign has 2 different meanings, logical OR and summation. When logical disjunction is in a micro-operation, then summation. When logical disjunction is in a control function, then OR. Example, P plus Q colon R1 R2 plus R3, R4 R5, logical disjunction of R6. List of logic micro-operations. There are 16 different logic operations that can be performed with 2 binary variables. The 16 Boolean functions of 2 variables x and y are expressed in algebraic form. The 16 logic micro-operations are derived from these functions by replacing x by the binary content of A and variable y by the binary content of registers B. 16 logic micro-operations. Some applications of logic micro-operations. Logic micro-operations can be used to change bit values, delete a group of bits, or insert new bit values into a register. The following examples show how the bits of one register A are manipulated by logic micro-operations as a function of the bits of another register B. Selective set. The selective set operation sets to 1 the bits in A where there are corresponding ones in B. It does not affect bit positions that have zeros in B. Selective complement. The selective complement operation complements bits in A where there are corresponding ones in B. Selective clear. The selective clear operation clears to 0 the bits in A only where there are corresponding ones in B. Mask operation. The mask operation is similar to the selective clear operation except that the bits of A are cleared only when there are corresponding zeros in B. The mask operation is an AND micro-operations. Insert operation. The insert operation inserts a new value into a group of bits. This is done by first masking the bits to be replaced and then ORing them with the bits to be inserted. The mask operation is an AND operation and the insert operation is an OR micro-operation. Clear. The clear operation compares the bits in A and B and produces an all zeros result if the two numbers are equal. Shift micro-operations. Shift micro-operations are used for serial transfer of data. They are also used in conjunction with arithmetic, logic, and other data processing operations. There are three types of shifts: logical shift, circular shift, arithmetic shift. Logical shift. A logical shift is one that transfers 0 through the serial input. The symbols SHL and SHR are for logical shift left and shift right by one position. Circular shift. The circular shift, also known as rotate, circulates the bits of the register around the two ends without loss of information. The symbols CIL and CIR are for circular shift left and right. Arithmetic shift. The arithmetic shift shifts a signed binary number to the left or right. To the left is multiplying by 2, to the right is dividing by 2. Arithmetic shifts must leave the sign bit unchanged. A sign reversal occurs if the bit in Rn-1 changes in value after the shift. This happens if the multiplication causes an overflow. An overflow flip-flop Vs can be used to detect the overflow. If Vs is equal to 0, there is no overflow. But if Vs equals 1, there is an overflow and a sign reversal after the shift. Arithmetic logic unit. An arithmetic logic unit, or ALU, performs many different arithmetic and logic operations. Steps in the design of the ALU are: design the arithmetic unit, determine the logic operations from the arithmetic unit, modify the arithmetic circuit to obtain the required logic operations. Combining the arithmetic and logic units. Now we have two pieces of the puzzle. An arithmetic unit that can compute 8 functions on 4-bit inputs, a logic unit that can perform 4 functions on 4-bit inputs. We can combine these together into a single circuit, an arithmetic logic unit, ALU. The arithmetic logic unit, ALU, is a common operational unit connected to a number of storage registers. To perform micro-operations, the contents of specified registers are placed in the inputs of the ALU. Combining the arithmetic and logic units. The ALU is a combinational circuit so that the entire register transfer operation from the source registers through the ALU and into the destination register can be performed during one clock pulse period. The ALU performs an operation and the result is then transferred to a destination register. It provides 8 arithmetic operations, 4 logic operations, and 2 shift operations. Each operation is selected with the 5 variables S0 through S3 and Cin. The first 8 are arithmetic operations and are selected with S3, S2 equals 0, 0. The next 4 are logic operations and are selected with S3, S2 equals 0. The input carry has no effect during the logic operations and is marked with Don't Care XS. The last two operations are shift operations and are selected with S3, S2 equals 10 and 11. The other three selection inputs have no effect on the shift. Arithmetic Logic Shift Unit. The 14 operations of the ALU are listed. Function table for Arithmetic Logic Shift Unit. Conclusion. In this chapter, we have covered the following aspects of register transfer and micro-operations: bus and memory transfers, three-state bus buffers, binary adder, binary incrementer, arithmetic circuit, logic and shift micro-operations, ALU.